Hello everyone. Today I wanted to start talking a little bit about game theory. So it's a very exciting subject and involves how human beings think. Right? So when we play games, of course, we are probably already thinking along the lines of what von Neumann and others have put down as game theory. But let's look at it more formally. And we will use this game theory when we study something about the Yoda freeloading attack. And you can also apply it, for example, to understand why miners actually do mining and follow the rules of Bitcoin. Right? And of course, it's a very developed theory, and we will only be scratching the surface. Okay. So here are some basics, and the resource for this is I got it from Investopedia. Right, you can find it online. So first of all, what is a game? So game is any set of circumstances that has a result dependent on the actions of two or more decision makers. So I'll write that down. Any set of circumstances that has a result dependent on the actions of two or more decision makers. Okay. And another definition, who is a player? Well, a player is any decision maker in a game. So what does the game involve? Well, these different players have some strategy. Okay, so of course there are some rules of the game, and the players have strategies. So what is a strategy? Well, a complete plan of action a player will take given the set of circumstances that might arise in a game. So a complete plan of action that a player will take given the set of circumstances that might arise within a game. Okay, so we will have to look at various strategies when we study the freeloading attack, right? And why do people follow the honest strategy? That's something we'll have to think about. So in addition to strategies, we have to have some sort of a reward mechanism, and effectively we will be saying what is that we'll have to think, what does a quasi-honest do, right? He wants to maximize his reward. So there has to be a payoff when certain events happen, and this is the reward a player receives from arriving at a particular outcome. So for a particular player, he gets a certain reward when from arriving at a particular outcome. Okay. So how are we going to consider all of these together, and because many different things can happen in a game. So we will use something called a strategy profile. So here, of course, here we talked about a strategy of a single player, but in a strategy profile, we will be considering a strategy of a number of players together. So this is a particular set of strategies So for example, the honest strategy for all players, that would be a particular profile. So particular set of strategies for all players which fully specifies all actions in a game. Right? So this is the basics, and in any game, of course, we can define things like strategies and strategy profiles and so on. Right? So a chess player, for example, might want to think that what if I play this move, then what is the other person going to do, right? But of course, the total number of strategies might be too high for a chess game, right? For very large, not infinity, but definitely very large. Okay. So how do we analyze these things? Because there can be so many different things that can happen in a game, right? If you think about a war strategy between two countries, there's so many different things the other army can do, right? And what we can do and so on, right? And if we do this, then what is the enemy going to do, right? So if we buy this many planes, then what is the strategy going to be of the other army and so on, right? So defense strategists have to think about all these things, right? And they would use ideas of game theory, right? So one of the concepts which you may be familiar with is something called a Nash equilibrium. So it's named after John Nash, who won a Nobel Prize, and there's even a movie about him which has come out. So what is a Nash equilibrium? It's a profile in which if any single player deviates, then he will stand to get a lower payoff. So let me write that down. The Nash equilibrium is a profile. So a profile, recall, is a set of strategies for all the players. Okay, and it has a peculiar characteristic, a profile in which if any single player deviates, he will stand to get a lower payoff. So taking the example of, let's say, miners in Bitcoin, so the example of miners in Bitcoin, let's say there is a profile in which all miners are honest, right? And if only a single player decides to become dishonest, if you can show that he will tend to lose more than if he were honest, then that is a Nash equilibrium, right? And intuitively, if you are already in a Nash equilibrium, then and players don't collude, they operate independently, then you would expect you would expect all the players to be in the Nash equilibrium, right? That because no single player is going to deviate from it, because he would tend to lose out. Right? So let's take a very famous example, something which you may have heard of. It is called prisoner's dilemma. Okay, so this might be used by the police, for example, to get information out of people, right? And in fact, these sort of game theoretic ideas are used for people. So they will, even if you don't have a game, they're just a single player, they might tell you that if you confess, your sentence will be reduced, or if you don't confess and you're guilty, then your sentence is going to be much more, right? Or if you reveal information about the other crooks who were part of the let's say some robbery or something like that, then we will give you a lighter sentence. And definitely the prisoner or whoever is arrested will have to consider all the strategies and see what is best for him. Okay? So let's look at the traditional prisoner's dilemma. So let's say that there are two prisoners, let's say A and B, and the options that they have, so they've been arrested for a supposed crime, so they can either they can confess or they don't confess. So this is for a single person, for a single player. Okay. And normally the prisoner's dilemma the police would question them separately. They would take A to one room and B to another room, let's say, and they would give them the option to confess or not to confess. Okay. Now, suppose the rewards are given in this way. So we are going to show all the profiles over here. And let's say these are the strategies that A can follow, and this is the strategy that B can follow. And so here A does not confess, and he has the option of confessing. Here B doesn't confess, and here he confesses. Okay, and what we're going to put over here is the payoff for both the players. and so let's say that this is the jail term. So let's say -1 implies 1 year in prison. Okay, and -10 implies 10 years in prison. Okay. Now suppose it's done in this fashion, so that if both confess to the crime, let's say it was a robbing a bank, each of them is going to get 4 years in prison. Okay, so I'm writing it as a tuple. This is A's and this is B's jail term. Okay, so we are writing it as a negative term because it's the cost. Okay, the cost is for jail term is negative. Okay. So if both confess, then they get 4 years in prison each. Right? Now suppose both don't confess. I mean, of course, here of course it's a direct done deal. You know, the police tell them we're giving you 4 years in prison. If both don't confess, then there is a chance that they are not convicted. You know, I mean, maybe the police will not find enough evidence against them, but still there's some chance that they find evidence and they will get punished. But the expected jail term would be, let's say, only 1 year. So let's write that over here. It's the so the expected jail term is -1 year, because expected prison term, I mean, it corresponds to 1 year, but we are writing it as -1. Okay. Because you know, like if they are convicted, maybe they will get 10 years each, right? But the chances that they are not convicted also may be high, because you know, the police may not be able to get enough evidence against them. Okay. So this they will have in their mind. Okay, they will have to sort of figure out that this is going to be the payoff. Now, what if one of them confesses? So here B is confessing and A is not confessing, and the police tell B, if you confess and A doesn't confess, that then you are going to be let off, no jail term. But A is going to be punished heavily. He's going to get 10 years in prison. Okay. And here, of course, everything is flipped. So they tell A, if you confess and B doesn't confess, we let you off, but we will punish him very, very severely, 10 years in prison. Okay. So both of them know that, you know, if the other confesses, then pretty much the chances of, you know, they getting convicted is going to be very, very high, because all the evidence will come from the other person. So these are their strategies. So for each of these squares corresponds to one strategy. Here the strategy is don't confess in the first one. Here it is don't confess, confess. Here it is confess, don't confess, and here it both confess. So the question is, what do they do? Right? I mean, it's a complicated choice that they have to make. And in fact, you will find that confession, given this particular payoff, you will find that both the prisoners will tend to confess, and they will both get 4 years in prison. Okay, which seems a little bit counterintuitive, because here, if both of them don't confess, then the payoff is better for them. I mean, the average term, expected jail term is actually less. Okay. Right, so maybe I should say payoff is the anyway, maybe I should put that to be more precise. I'll just say it is the payoff is negative of the expected j term. Okay. So it's very interesting that instead of choosing the option of don't confess, they will go for this, right? The question is, why does that happen, right? And you have to keep in mind that they are being questioned separately, so they are not in the same room when they decide whether to confess or not to confess. If they could collude with each other, then they would choose this one because it gives them the best option. But if you keep them in separate rooms and give them these two choices, they would tend to do this. Yeah, and that's what we want to understand why this is the case. Right? So let's see if one of these is a Nash equilibrium. So let's look at the first profile. Don't confess, don't confess. If one of them deviates, let's say B deviates, will he lose money? I mean, so you would want that any one of them, if he deviates, he should lose money. So if B deviates, his payoff goes from -1 to 0. Okay, so he's going from don't confess to confess. And similarly, if A deviates, so we are saying only one of them deviates. If A deviates, then he is also going from -1 to 0. So this is not a Nash equilibrium. Okay, because we want a Nash equilibrium such that if any one deviates, then he would tend to lose out. Let's look at another one. Let's say that we look at this one. So it is don't confess, confess. Okay. Now let's see, suppose A deviates, so he goes from don't confess to confess. Then it goes from -10 to -4. Okay, and if only B deviates, so B deviates means he goes from confess to don't confess. A's strategy stays the same. So he goes from, his reward goes from 0 to -1. So this is a loss for B, but here there is a gain. Okay, the payoff is better because the prison sentence decreases. So this is again not a Nash equilibrium. Okay, and from symmetry we can say that about CDC also. What about the fourth one? Let's think about this. Where both confess. If B changes its strategy, then it goes from -4 to -10. And if A changes its strategy, only A changes its strategy, it goes from -4 to -10. Okay, so both would actually tend to lose out. So if only A deviates, his payoff goes from -4 to -10. Okay, and similarly for B. So this is a Nash equilibrium, because if any single player deviates, and it's true for all these players, then they would actually lose out. And so this is the intuition about why people choose this strategy, because it's a Nash equilibrium, right? So another way to think of it is in terms of something called a dominant strategy. So what is a dominant strategy? So let's look at this for a moment and go into the minds of one of the prisoners. So suppose they are separated, they are in different prisons, and so A is going to think, suppose B follows a particular strategy, what is the best thing for me to do? So suppose B says, suppose A is thinking in his mind, suppose B chooses don't confess, then what is the best thing for me to do? Right? So he has to consider among these two. If he follows don't confess, he gets -1. If he follows confess, he gets 0. Okay, so it's better for him to confess if B is going to follow the don't confess strategy. Suppose he thinks, suppose B chooses to confess, what is the best thing for me to do? Okay, so now I have to compare between these two. That's what A is going to do. Suppose he chooses don't confess, he gets -10. If he chooses to confess, then he gets -4. Right? So again, confess is a better solution. Okay, so we're not thinking of it in terms of Nash equilibrium here. We are thinking, suppose there is a fixed strategy. Suppose B has chosen one particular option. What should I do then? Okay, and if it turns out that one particular strategy, like confess in this case, is the best thing, then that is called a dominant strategy. Okay. So let's write down the definition. So a strategy that maximizes the payoff of a particular player for any fixed strategy of the other. Okay. Okay, so for A, confess is a dominant strategy. Okay, because his thinking is as follows. So fixed strategy of B so he could say don't confess, or he could say confess, right? And it turns out that in this case it's better to confess. And here it is also better to confess. So it's the same strategy. So the same strategy of A is better for any particular fixed strategy of B. Okay. Though if they were able to completely collude, they would both say don't confess. Because we are preventing this collusion, and both of them are smart people, right? They are rational people. They will decide to confess. Okay. So there are two ways to think about this. the prisoner's dilemma. Okay. And why is it called a dilemma? Because, well, they have to figure out what to do. They are in a dilemma, they don't know what to choose. Okay, but given that particular payoff, they are going to do something counterintuitive, which is to confess. So one way is to look at that there is a single Nash equilibrium exists, which means that if the players are rational, they will opt for it. Okay. And the second thing is, if a dominant strategy exists for a player, it opts for it. So this is the basics of game theory, and we will next use it when we talk about the freeloading attack. Right? Of course, game theory itself is much more tricky. So we'd have to think. I mean, this prisoner's dilemma is sort of an easy situation, but a real situation might be much more complicated. And let's say that the players start out and they are not in a Nash equilibrium, then will they go towards a Nash equilibrium? Right? What is their behavior going to be? Right? And that's much more complicated. These game theorists look at stochastic situations and so on, and they see whether the players are going to converge to a particular equilibrium of some kind. Right? And in the real world too, I mean, all these ideas are very useful because you see sometimes the stock market crashing. Why does that happen? So people are initially very confident, and then suddenly things go down. You might find the market crashes when everybody wants to sell. They are worried about their money. Right? And some of these game theory ideas could help over there, to understand these sorts of situations. Right? Because it's sort of a prisoner's dilemma situation where they have some sort of strategies in mind, but maybe they are not colluding with each other. Each person is working independently. And once he sees that other people are losing confidence, then he himself changes his strategy. Right? So that's more like a dynamic situation. It's not like a prisoner's dilemma where you have one person, one particular choice to confess or not. So it's over time, you're changing your decisions. And it may so happen that everybody loses confidence and they all sell, in which case you have a market crash. Right? So we will next study the freeloading attack. So we are going to call a profile in which all QH, all quasi-honest nodes behave honestly as A. So if all quasi-honest nodes let's say behave honestly, then we call the profile A. So this is the typical notation used in game theory textbooks. Okay? So essentially what we're going to try to analyze is that we consider this particular profile and we try to show that it is a Nash equilibrium, or under what conditions it's a Nash equilibrium. So if at all it's a Nash equilibrium, we saw earlier that intuition tells us that everybody is going to try to stick to this Nash equilibrium. Right? So how are we going to do this? Well, we'll have to analyze. So suppose we are in this profile A, what is the reward that these quasi-honest nodes are going to get? Okay. So we said that by design, probability that Byzantine adversary wins is at most beta. Okay, so let's assume for the moment that it is beta, the worst case. Okay. So remember that in this model we have quasi-honest nodes and then we also have a Byzantine adversary. In an earlier model we had perfectly honest nodes and a Byzantine adversary. Okay. So what is the reward that these quasi-honest nodes are going to get in this particular profile? Okay. So let's say, so we suppose that the deposit of each node is some D, and let's say that the reward that each QH node gets if its solution wins, is let's call it W. Okay, so suppose everybody behaves honestly. It's just like the earlier analysis where we had honest and Byzantine nodes. Then of course they don't always win. There's a small probability that the adversary wins, right? But if they win, they get reward W. Yeah, and of course we will have to decide what this W and D are going to be. What are good incentives to ensure that indeed this profile A is a Nash equilibrium. So the expected reward for a particular quasi-honest node, let's call it I, is, and we are again going to use notation typically used in a game theoretic textbook. Okay, so they talk about utilities. So we have put sub I, which is the node number. So the utility that node I is going to get in this profile A, which means that profile A means everybody is honest, is 1 minus beta times W. So I get W if we win, and there's only a probability of 1 minus beta of everyone winning. Okay, plus beta times that the adversary wins, in which case we lose our deposit. And what else is the cost? Well, we are going to call it C1, which is the cost of doing the computation. So everybody is honest in this particular profile, which is why they are doing the computation. So this is the reward that honest nodes are going to get, the expected reward in profile A. Okay. Now we have to look at a profile in which any one node is going to deviate from this. Right? That's how we look at Nash equilibria. So we are going to define another profile in which only the QH node I does a freeloading attack. So what does this mean? So node I is going to contact ES nodes of previous rounds and tries to guess the solution. Okay. So this is what it's trying to do. It's a little bit lazy. It's going to essentially try to save on this computation cost. Maybe the computation is heavy because after all it is a CIT. So it's a bit lazy, and so it just wants to contact people from previous rounds in order to guess what the solution R is for this particular round. Okay, let's say in its own round. Okay, so let's say that this communication cost is C2. Right? So the way we've designed the protocol, it's not easy to guess R given that you contacted people in the previous rounds, right? Because R changes from one round to the next. So let's say that there is some probability of getting it correct. So the probability of QH node I guessing R correctly is some gamma. Okay, and for the moment we are going to say we don't know what gamma is. We just leave it as this parameter. And we'll just say that the Rice algorithm makes this gamma small. Right? So now let's look at different cases. So if the QH node I guesses the R value correctly, okay, then what is its reward? Okay, so then it is almost it's almost similar to behaving honestly. I shouldn't say behaving, let's say computing honestly. So the reward is 1 minus beta times W minus beta times D. Right, of course when we take the expectation we have to multiply by gamma. And secondly, if it guesses wrongly, then what happens? Then let's say that the worst happens, then it loses its deposit, right? So so that means the reward is minus D. Okay, so that means, so what is the utility in this particular profile? Okay, so A minus I is this profile. This is again the notation typically they use in game theory, that if one particular node, one particular player in the game I deviates from a particular profile, you just say A and minus I. Right? So that means this is going to be gamma times 1 minus beta times W minus beta times D plus 1 minus gamma times minus T minus C2. Right? This is the communication cost. So for A to be a Nash equilibrium, we want UI A to be strictly greater than UI of A minus I. Right? So that if any one person deviates, then he would be worse off. He's better off sticking to profiling. And if you do the analysis, you've done it in the paper, this ends up being that the deposit plus the reward should be greater than C1 minus C2 divided by 1 minus beta times 1 minus tau. Okay. So beta is chosen to be very small, and Rice algorithm also tries to make gamma very small. So effectively these two are 1, so that is nearly equal to C1 minus C2. Okay. So all we have to do is, we might have some idea of what this computation cost is, but suppose even this is 0, all we have to do is to ensure that the reward for doing the computation and plus the deposit value is going to be greater than C1 minus C2, and then we are safe. We know that this is a Nash equilibrium. So if the quasi-honest nodes are rational, they will tend to stick to profile A rather than trying to do something like a freeloading attack. Okay. So of course we've made a lot of assumptions. We are saying that there is no collusion between nodes and so on, right? But at least it's better than assuming that nodes are perfectly honest, because in the real world, in a permissionless setting, nodes are indeed rational. Yeah. So with this I wanted to end the discussion on game theory. We'll use some of the ideas later on when we talk about proof of work, right? And in the next class I wanted to talk a little bit about some of the experiments we did for Yoda and show why we do experiments in this sort of research, systems research, because we will see things that we would not have sort of imagined just by theoretically thinking about things.